So a planar graph is a graph where you can draw it so that none of the edges cross. If you already have a graph where none of the edges cross, automatically it's planar, no big deal, you don't have to do anything else. Now, if you start off with a graph where the edges are crossing to begin with, still can be planar, you just have to figure out if it is or not. Now, if you redrew your graph and it now has no crossing edges, that's then called the plane graph, or a planar depiction of your graph. In other words, it's the graph you started with, but you redrew it. There's your plane graph. Now, you can also, if your graph starts off and has edges that are not crossing, automatically it would be both a planar graph as well as a plane graph. Now, last time, it looks like the program's frozen. Just a second. Last time, as well as the time before, we also talked about the dual of a graph. This only is applicable to graphs that are planar. It does work both for simple planar graphs as well as multi-graphs that are planar. You just have to be able to draw the graph so that none of the edges cross. You don't deal with duals with directed edges, so these really are the undirected edge graphs. Okay. And this is what we did quite a bit, where we converted faces into vertices. We changed up the edges, where every edge, when we drew the dual graph on top of the other graph, the new edges crossed the old edges, so number of edges stayed the same. And this is where the number of edges and the number of vertices flip-flop between the original graph and the dual graph. Okay. We talked about bounded faces, we talked about unbounded faces. Faces are determined by circuits, but not every circuit in your graph, only the ones that, if you draw them out, you're not going to have any vertices inside the region that's defining the face, or that's considered the face. And that's true of both the bounded faces as well as the unbounded faces, and you only ever have one unbounded face. Now, that's where we've been in the past. Okay. So here's some of the other new stuff, and I believe we ended, I think Theorem 1 is the only one that we did previously. Theorem 1 dealt with what one of the questions was just a little bit ago. A graph is considered planar if and only if it does not contain a subgraph that is a K5 or K33 configuration. So this totally ties into that circle chord method that we looked at. And in fact, this works even if you don't have one big circuit that grabs all of the vertices in your graph. Okay? So if you're able to find any little K5 or K33 configuration, even if the circle chord method fails, this guy still works. Now, we're not going to talk about any of that today. That was just our running start. What we're going to look at is Euler's formula. So Euler's formula says you have a graph. The graph has to be both connected and planar. Now remember, we talked about something with disconnected graphs a little while ago. And one of the things that we said when you have a disconnected graph, your disconnected graph is comprised of different components. Each component is itself a connected graph. So Euler's formula would actually apply to each component of a disconnected graph as well. Okay. Now, suppose you have a connected and planar graph, then any plane graph depiction of this graph. So note, if your planar graph is currently drawn so edges cross, you have to uncross the edges before this stuff works. Okay? So then what you get is a formula. And the formula is, and this is the standard way it's written, F equals E minus V plus 2. And here's what all that means. So F here is number of faces. Your book doesn't use the word face, he uses the word region. So when he wrote out Euler's formula, he actually put an R instead of an F. So if you see little R's dancing around in your textbook, especially in section 1.4, don't freak out. It's really just the number of faces. Okay. E is representing the number of edges, and V the number of vertices. I have on purpose tried not to use that notation in the past with you guys, but it is really, really common to represent the lowercase e and the lowercase v as the number of vertices and the number of edges in your graph. In the past, we've been doing it in set notation, but this is super duper common too. But it's also super common to use lowercase e and lowercase v as the name of a vertex or an edge, which is why I've been trying to avoid it, so you didn't have two different things, the same symbol representing two different things. Okay. Now, it turns out there's a corollary of this theorem, and what I went ahead and did is I went ahead and put all the facts at the beginning, and then we'll have examples for the rest of the time. Okay. So the corollary to this formula goes as follows. You start off and you have a connected planar graph. So totally connected graph. The graph, maybe the edges currently cross, maybe they don't, but it's planar so you can uncross the edges. Then, turns out as long as you have more than one edge, okay, so somebody that you could potentially have crossing edges, okay, then it turns out the inequality that number of edges is less than or equal to 3 times the number of vertices minus 6 is always true. But here's the condition. You have to be in a connected planar graph. So this guy right here could totally be violated. If you have more edges than 3 times the number of vertices minus 6, what would that mean? That would mean that your graph is either not connected, unlikely, I guess it could, or it is more likely not planar. So this here with the too many edges, so if the inequality breaks, the too many edges typically tells you you're not planar. Why? Too many edges, you can't uncross the extra snarl of edges. Now, before we get to examples, we do have to do one more definition, and this definition is the degree of a face. Your book also talks about this in the context of a boundary of a region. It's, in both cases, referring to the edges that are creating the circuit of your face. So remember over here, suppose you have some face. I'm going to be lazy and just draw a little square. If this is your face, then the degree of this face, since there's only one of them, I'm going to call it F, would be 4. Wow, that's a terrible 4, isn't it? Pretend that's a 4 while I go and rewrite it. 4 because there are 4 edges comprising the boundary of that circuit. Here we go. All right, so first example that we have is going to be that little guy. And that little guy is, well, I'm not actually going to read out the full graph there. But in terms of that guy, what we want to do is we want to look at, we want to find all the faces. So first of all, look to see where if you can find all of the faces. And then the second thing we're going to do is to find the degrees. Okay? I'm going to give you guys a second to copy down the graph and see if you can come up with a guess for the number of faces and the degrees of each face. And then we'll start talking back together again. To answer your question, not exactly. I actually just looked it up to confirm. It's dealing with the complete bipartite graph on K33, and the complete bipartite on K33 is your smallest bipartite graph that's non-planar. The inequality doesn't work for planar graphs. Now, does it not work for most bipartite graphs? Yeah, because most bipartite graphs aren't planar, but the issue isn't the bipartness of the graph. The issue is the non-planar part of the graph. So that's the tie-in with the bipartite graphs. All right, so at this point, I'm going to assume that most of you have looked at this guy and come up with a guess. So let's go ahead and label our faces. So I'm going to assume that you guys found at least one face. One of the faces is the unbounded face. When in doubt, there's always that guy. Now, I'm going to claim there's 2 more faces. One of them is the little itty bitty triangle on the inside. And the other one is the stuff around the outside of the triangle. So do a quick check. Make sure I did not miss any face. All right, not that you guys fussing about me missing any face. So let's go ahead and count up everything. We came up with 2 bounded faces and 1 unbounded face, so a total of 3. Did anybody happen to count up the number of edges in this graph? I'm getting 8 for edges. You guys get 8 too? 1, 2, 3, 4, 5, 6, 7, 8. And as long as I didn't miscount, it looks like there should be 7 vertices. If that's wrong, somebody shout out. Okay? So now we're not going to worry about the dual of this graph, although you totally could do it if you wanted to. If you did the dual of the graph, you'd have only 3 vertices and 7 faces and a whole bunch of edges. That would definitely be a multi-graph. Okay? If you were dealing with the dual, you would pick up a loop in the dual. So F1 and F2, you'd have 1, 2, 3 edges between them, so that would be a multi-edge. And F2 would actually, you'd have to have an edge that crosses C to G. So that guy would, in fact, have a loop that goes from F2 and then back to F2 again. So that's how you pick up loops in your dual. Let me actually, this might help. Let me shade in these guys. What would be a good color here? Here would be a decent color, maybe. There's this guy. And then there's, let me do a different color. Try not to make it too obnoxious here. I'm regretting this already. Remember, you're dealing with these guys. I guess I should say cycles to form your faces. Okay, so those, the yellow one and the blue one would be your 2 bounded faces, and then your unbounded one is still, I didn't change the white. EGF. But not the way it's drawn. So in this particular case, if we just take the way it's drawn, those would be our 3 faces. All right, so thing that we want to do here is I just want to do an illustration of degree of your faces. So if we actually computed these guys, suppose we did something like, oh, we do not want to keep a highlighter. So suppose we did the degree of face 1. Anybody got a guess on the degree of face 1? So face 1 would be 3 because it deals with that little thing that looks like a triangle. Anybody have a guess on the degree of the unbounded face? I've got 2 guesses for 4 so far, and more of them coming in, so that looks pretty good. And the hardest one for this one is to find the degree of face 2 or F2. I see there's a couple of guesses for that one. So let's actually count these guys up together. And this is why I grumbled to myself about already highlighting things. So I'm going to go and see if I can't remove the blue highlighting. No, please just that. No, undo. Okay, so we can't remove the blue highlighting easily. Okay. So let me just get a different color and we'll make it horribly obnoxious different color. What is a horribly obnoxious different color? I don't really have one, but maybe a fat green. So it'll look terrible. So if we start at, say, I don't know, how about C because my pen's already there. We've got 1 edge for F2, 2 edges for F2, 3 edges, 4 edges, 5 edges, 6 edges, 7 edges, 8 edges, 9 edges, and we're back. So yes, that would tell us, as several of you guessed, we are going to get a degree 9 for this guy. Okay. Now, there's something weird about what we just did. Anybody notice the weirdness of what we just did? The degree of the face will depend on how your plane graph is drawn. Yes. And yes, the actual weird thing is that edge that several of you pointed out, that edge that includes C and G, we actually counted it twice, or we used it twice. That'll happen anytime you have what essentially is a bridge, okay, where you've got this component and your face is actually on both sides of that component. Okay. Why would I say this edge is a bridge? If you remember the definition of a bridge, if you deleted this edge, you would have a disconnected graph. If you did move the internal bits, so let's redraw this. I'm not going to claim that this is an awesome way to redraw this graph, but since several of you have mentioned it, oh, it's terrible if we're drawing it. There's attempting to be the outside bits. So A, B, C, D. And then from C, we have the little triangle place. And this one is G, F, and E. So if we label these guys, we have F2. Oh, I should go back to black. Just a second, just to keep this stuff consistent. F1, and the unbounded face is still out here. Now notice there's things that change, okay? So for this one, the degree of F1 is still the same. But what about the degree of F2? It's now going to be 4, and anybody spot what the degree of the unbounded face now turns into? So let's check it out. So if you're looking at your unbounded face, and let's actually draw through this, I'll get another sort of puffed out thing. Oh, let's do it lighter so it's not quite as obnoxious. So here, unbounded face, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So you would get back to 9. Nope. It's just two different plane graph depictions of the same planar graph. Now, since the degree of your face does actually change depending on which plane graph depiction we use, when you're looking in terms of these guys, yeah, they'll switch around, but notice if you add them all together, what happens? The total sum of the degrees are going to stay the same. Yeah, because you're still using all of the same edges. It's just you labeled the faces differently. That's as simple as you could have flip-flopped the labels. But it's also orientation-wise, you're going to have a one-to-one mapping between these two. Yeah, because as a couple of you guys noticed, there being two different depictions of the same planar graph means they are automatically isomorphic. So you're going to have all the same characteristics, but your labels will be a little bit different. Okay? So when we're dealing with degree of faces, you're counting up all of your edges, which means regardless of whether the edge is incident to face 1 or face 2 or the unbounded face, it's still being counted. And notice how many times it's being counted. This little face on the inside, the edge that's incident to that face is counted once for face 1 and 1 time for face 2. If it's over here, that same edge, EF, is counted once for face 1 to get the 3, and once with the unbounded face to get the 9. In terms of a loop, the loop was only in the dual. Okay? So notice each one of these edges that you're dealing with, that edge will be counted in the degree exactly twice. Once for the face on one side of the edge and once for the face on the other side of the edge. Or if you're over here, once for the face on one side of the edge and once for the face on the other side of the edge. Now, if we notice our funky edge, the one that was a bridge, this guy here, GC, or in the first depiction over here when they're nested, what happens? That edge is also counted twice, but because that edge is part of the same face, it's counted twice in the degree for that same face, whether it was the unbounded edge face, or face 2. Okay. Now, what does that mean? What I'm trying to get to is if you add up all of these degrees, what happens? We've counted every single one of our edges, but what's this sum? And I'm just going to do it for one of these. Well, 3 plus 9 is 12. 12 plus 4 is 16. And notice, how does 16 compare to our number of edges? It's exactly what? Don't say the same. Yeah, it would be exactly twice. So what this would mean then here is we actually get the following result. And the following result here looks almost identical to one of the results that we had previously when we talked about degrees of vertices. It turns out the same thing happens when you're dealing with the degrees of the faces. If you add up all the degrees of the faces, whichever plane graph depiction you used, however you actually wrote it out, when you added up all of those degrees, you should always get twice the number of edges in your graph. Now, notice, if you accidentally forgot to count an edge twice, what would happen? When you added these up, you wouldn't have twice the number of edges, so that's also a quick check to see if you actually calculated your degrees correctly. Okay. So that's one example of dealing with this stuff. So let us look at another example. But before I go to that next example, any questions from you guys? Yes. People typically write them as two different things, so let me actually write down all the formulas we have so far. So the formula with the degrees of the actual vertices is 2 times the number of edges. We also have Euler's formula, which is number of faces equals number of edges minus the number of vertices plus 2. Notice we can actually check that over here. Number of edges is 8 minus number of vertices gives you 1 plus 2 gives you 3. And this is a planar graph. These first two right here work in pretty much any graph. Wow. As long as you have undirected edges. This one here only deals with planar graphs. And the corollary, which is the inequality, E, number of edges, is less than 3 times the number of vertices minus 6. For this one, the graph has to be planar as well as connected. Connected has an O. Okay. So those are the results that we've got so far. No. So in terms of standard notation, even though technically in terms of set notation, you would want the cardinality symbol or the guys that look like absolute values. In graph theory, you actually use lowercase e, v, and f to represent the number of faces, edges, and vertices. So yes, these two are considered the same exact thing. I've been on purpose trying desperately to avoid using these symbols for you guys because we also use them to represent the elements of a face, an edge, a vertex. And personally, I think when you're just starting off with it, you don't need to have the fact that we use the same symbol to mean two different things really thrown in your face. But I'll go ahead and keep those formulas up at the top, and when we move on to the next questions, I'll write them to the side too because we're going to need them through the rest of this section. So next example that we have doesn't start off with a picture, it just gives us a description, and this is similar to some of the examples that we looked at in section 1.3 when we were checking how many vertices or how many edges do we have when we were using that formula that came from section 1.3. These three come from section 1.4. Okay? So suppose you have some graph, and you know it's got 12 vertices, and you know that every face has 4 edges. That tells you what? This tells you so far that the number of vertices, use either symbol that you want, is 12. This also tells you that every face is defined by 4 edges. That tells you that the degree of each face is 4. And what we want to do is we want to find the number of edges and the number of faces that you have to have in the graph in order for this graph to be connected and planar. Okay? So what we're going to use is we're going to use as much of this information as we can, but we've only got those 4 formulas really to work with. So let's write out everything we know, and we'll pull this stuff that's in Scratchwork down to the proper format. The first thing is starting off with what we know. We're told that we know for sure that the number of vertices is 12, and I'll go ahead and use the lowercase v here. We're also told that the degree of each face is 4. And here's what we want. We want to have connected planar graphs, so we want to be able to have, the inequality of number of edges is less than or equal 3 times the number of vertices minus 6. And we also want Euler's formula. So to illustrate this one, these are all of our faces. So if this is F1, degree of F1 is 4. And that's actually going to be true for all of our faces. Now, what else do we have? So first thing is, let's actually start with a formula that we know we can deal with. We know we have a number of vertices. We know we have a degree. So we know some things. Okay? So let's start off with this equation. Yep, we could actually do that one. So let's pull that one over here to the side because we're not going to need it first, but we will actually need it. Since we do know the number of vertices is 12, this does tell us that if we want to have a connected planar graph, in other words, in order to have a connected planar graph, we'll go ahead and plug in 12, and that does, in fact, give us 30. So this means that we have to have fewer than 30 edges in our graph. Now, it does not tell us we have exactly 30 edges in our graph. It just tells us we're going to have 30 or fewer. So if we then go ahead and strategically walk through these formulas, if we look at the degree of all of our faces and add them up, well, we don't know how many faces we have yet. So we'll go ahead and start plugging some things in. We do, however, know that it would be 4 times however many faces that we actually have. And on the other side, we're then going to have 2 times, and I'm going to replace this symbol of the absolute value of capital E, so number of edges, with that lowercase e that all the other formulas have. Okay? So this then gives us a relationship between the number of faces and the number of edges, and because they both have a multiple of 2 on both sides, I'm going to go ahead and simplify and say that this gives us the relationship of the number of faces times 2 is the same as the number of edges. So this is a piece of information that we're going to need. So I'll go ahead and box the pieces of information that we're going to need to worry about. Okay? Now, after you have this relationship between the number of faces and the number of edges, I'm going to go back and use Euler's formula. Now, Euler's formula says the number of faces equals the number of edges minus the number of vertices plus 2. We already know how many vertices there are. And now we can rewrite the number of edges in terms of faces. So we're just going to plug in. Let me go ahead and box this guy up here. So if we plug in, we'll still have the f on the left-hand side, but now we'll have 2 times f minus 12 plus 2. At this point, one unknown, one equation you can totally solve for f. So if we solve out for f, what happens? Move 2f to the other side, so we'll have negative f equals, what is that, negative 10? So this tells us we should have 10 faces. Okay. Now, once you go ahead and you have your number of faces, I'm going to claim we can totally find the number of edges. What do you guys think? How many edges do we have? I'm going to highlight that because we've boxed the other answers. That's half of our answer. Yeah, exactly. So here, ooh, almost. You went the wrong way. The number of edges, I'm just going to pull from the box guy up here. Number of edges was twice the number of faces. So this would give us 20 edges. Let's highlight that. Now, once you get your number of faces and your number of edges, you do want to do a check. Okay? So this here, that's the answer. But before you finish and actually say, yep, for sure, that's the answer, do your check. What's your check? Up here, the thing that we hadn't touched before, our inequality that says every planar and connected graph has to have the inequality of number of edges less than or equal to 3 times the number of vertices minus 6. We said that in our situation with our 12 vertices, that meant our number of edges had to be no bigger than 30. So with our answer, did we actually meet that inequality? You got it. 20 is definitely less than 30. So that means that last check to make sure that this really did work just fine. In other words, confirm that we had both the connected and the planar graph. There was nothing that automatically flagged that there's anything wrong there. you go and you check this inequality. Now note, this inequality rarely will get you to actually, what's a good way of phrasing this? This inequality will rarely get you to actually solving for the number of edges or vertices or faces or whatever. But what it does do is if your number of edges or your number of vertices breaks the inequality, it'll tell you that the situation either doesn't work, you can't get to a graph that is connected in planar with those conditions, or in this case, if it meets the criteria, you're like, yep, the math looks like it works, we're good. Yeah, so the answer to your question is, if you checked here and we gotten 40, that would say, nope, sorry, the only way that this worked is this number of edges was 40, and that doesn't happen in a connected planar graph. So. All right, so that's that example. The next example I've got is similar. Okay? So suppose you have this next guy. It's very, very similar. So this next guy says we want to find a connected planar graph. So notice the differences in the wording of this example, or this next example. The last one, the wording said, find the number of edges and faces. So all we had to do is once we found the number of faces and found the number of edges, we were done. This one actually says find a connected planar graph, and then it gives the criteria. This here, if you had this in one of your questions, this actually means build the graph or draw the graph if it's possible to do so. So this part here, find a connected planar graph. This means draw the graph. And the caveat is, of course, if this graph exists. So if it can exist. So in this case, we're going to try to check to see what happens. And if we're able to find said graph, we'll draw a picture. If we're not able to find it, we'll say, oh, sorry, this graph doesn't exist, and then you don't give any picture. So first thing is pull out the given information. So yep, we are told that we have the 17 faces. So we've got 17 faces, and we are told that every vertex, and notice it's back to vertices now, has the degree 5. So I'm going to write that in 2 steps. So the degree of all of our vertices equals 5, and that's for all vertices. So then when we start looking at our formulas, and let me put the formulas over here to the side, although some of you have already started to look at them. The sum of the degree of your vertices is twice the number of edges. The sum of the degree of any faces, although it doesn't look like we're going to need that one, is also twice the number of edges. We've got Euler's formula, which is number of faces equals number of vertices, number of edges minus number of vertices plus 2. And then you've got that inequality that I really don't want to say again, but I put it over there to the side. Okay? So in this case, when we start using this information, we now have that we're looking at the degree of vertices. So when we start tying stuff together, the formula that would be the smart one to use is that very, very first one that talks about the sum of the degrees. So here, I'll go ahead and rewrite the formula. So if you take any vertex, or really every vertex in your graph, and add up all those degrees, it's supposed to be 2 times the number of edges. We have no idea how many edges there are, but I'll go ahead and use the symbol lowercase e, which is one of the standards. Now, what we do know is we have 5 times the number of vertices in our graph, 5 because of degree 5, number of vertices because each guy had degree 5. Okay. Now, at this point, this is similar to what we had before where we were able to relate in the last problem, number of edges to number of faces. Here we've got number of edges relates to number of vertices. Okay. And actually, we probably should solve for one of these two. So and I shouldn't have boxed that probably. So let's instead go ahead and solve for one of them. I don't know, maybe solve for e, because 2 is a smaller number. So this would tell us that the number of edges is 2.5 times the number of vertices. Now, notice what these first 2 summation formulas are giving you. In both this example and the last example, which are the 2 classic ways, of using this stuff, we were just getting what? We were just getting a relationship between two of our unknowns, between the number of edges and the number of vertices, between the number of vertices, number of faces and the number of edges. Why? Because in Euler's formula, there's three unknowns. We're looking at faces, edges, and vertices. So while we're given up here just the number of faces, we can't solve for two unknowns in one equation. So you have to use a helper equation to get a relationship between the unknown number of edges and vertices. But now we're ready to use Euler's formula. So if we go ahead and use Euler's formula, I'll write it out largely over here. You can just go ahead and drop in your numbers. So we know we have 17 faces. For edges, we don't know how many, but we know that 5 over 2 times the number of vertices is going to be the same as our number of edges, and I copied everything else the same. And at this point, it's just solve for the number of vertices. So what is it? If we combine the number of the two terms v together, that should be 3 over 2. Subtract 2 from both sides, that should be 15 equals 3 over 2 times v. So this means that v is what? 2/3 times 15, which should be, I'm getting 10. Are you guys getting 10? All right. So this tells us the number of vertices that this graph should have is 10. Now, why would we even be thinking about solving for the number of vertices in our graph? Because there is no way that you can actually draw a graph if you don't know how many vertices you're going to have. Not going to lie, if all you know is the number of faces, it's kind of hard to draw the graph too. So in order to draw the graph, we need to be able to find the number of vertices that we need. We also really need to solve for the number of edges. So with the information that we have so far, could we actually solve for the number of edges in our graph? What do you guys think? Yep. So I'm going to use the formula, and I'll do it in 2 steps. So the formula that we had from previously said the number of edges was 5 seconds times the number of vertices. So yep, we would totally get 25 edges is what we're supposed to have. Now, before you start going and you're saying, hey, I'm totally going to draw a graph that has 10 vertices and 25 edges, and I'll put those edges in such a way that I have 17 faces. Yes, feel free to be overwhelmed at this point. That's okay. You want to check to make sure that you can actually get a graph with those criteria. So let's go back to make sure what criteria we need. We know how many edges, we know how many vertices, and we know how many faces this graph is supposed to have. But this graph is also supposed to be a connected and planar graph. Now, Euler's formula works with planar graphs. Okay? So that's fine, no worries. But in order to be both a connected and a planar graph, you're also going to have this inequality satisfied. We haven't checked that yet, so let's go and check to make sure that our inequality is satisfied. If this inequality is satisfied, that means we're probably going to be able to draw a graph with our, 10 vertices, 25 edges, and 17 faces. We might be grumbling and really don't want to, but it should be possible if that inequality works. So I think I have enough space to put that inequality at the bottom here. So let's go ahead and check our inequality. So we're supposed to have number of edges is less than or equal to 3 times the number of vertices minus 6. Our number of edges was 25. I'm going to put a question mark here because we haven't actually verified it yet. Number of vertices was 10. So if we simplify that side on the right, what are you guys getting on the right-hand side? Yeah. Now, check that inequality. Is our inequality correct? Yeah. So that would be the conclusion. The conclusion here is that with this number of vertices and edges, you can totally have a graph with that number of vertices and edges, but it's not planar. So this one here won't give a planar graph. So what does that tell us about our conclusion? Can we actually draw a connected planar graph with 10 vertices and 25 edges? Because remember, the question asks us to find the graph. Yeah, so the answer that you give is there isn't one, or properly, no such graph exists. And that right there is the big way that that inequality is used. It's a way to point out, hey, with the pieces and parts that we've gotten perhaps too involved with the algebra determining, those pieces and parts really aren't going to yield a planar graph. And if you don't have a planar graph, all of a sudden, well, we're not going to be able to get the thing we wanted. Huh? Questions make sense? Kind of feeling okay in terms of manipulating these formulas? Hopefully the answer is yes, or sort of. But even if not, I've got one more example that looks similar. This one here focuses in on that inequality a little bit more, and it also has a little bit different wording with respect to faces, which is why I wanted to make sure to cover it. So this one here wants to know, I feel like I've missed something in terms of the, it wants us to see if this statement is true. So this one here says that the statement is, if you have a graph G, and this graph is both connected and planar, and here's the other key thing, the number of edges is as much as possible, or as many as possible. Remember, the inequality is this exact same thing, except number of edges is less than or equal to. So if the number of edges equals 3 times the number of vertices minus 6, this means that you have as many edges as possible and the graph still is planar. So what does this say? This says then every face in the graph must be triangular. Now, before we go too further, if we're talking about a face is triangular, anybody have a guess on what that means? Yeah, there's a couple of different ways that you can refer to it. It actually means if you look at your faces, they all look like triangles. Or as you guys said, your face is comprised of 3 edges, it's incident to 3 edge, or it is the face has degree 3. Okay. Now notice, what happens if you didn't have a face that was degree 3? Okay? Suppose you had a face that was, so if, I'm going to just be lazy and do 4. You had a degree 4 face. Well, I'm going to refer here to bounded faces just because they're easier to deal with. You can do the same thing with the unbounded face though too. It's just harder to picture. If you have a face and it's inside of that square, so pretend you've got this graph, and maybe the graph is a lot bigger and this is just one face, or maybe the graph is just those 4 vertices and those 4 edges. Could you add in an extra edge and still have the graph be planar and connected? Yep. The fast one that people see is this guy right here. That would then cut your face into 2 pieces, and notice now both of those 2 faces are triangular, or they're now degree 3. Now, second thing you can do, notice here with this new guy, and now suppose you're looking at it as a full complete graph. We now have 2 bounded faces, both triangular. If you look at the unbounded face, so considering this is a full graph, what's the degree of the unbounded face? It still has degree 4, and I'm going to claim there's a way to fix that too. So notice that big fat curvy edge I put in there? Is the new graph with those 2 extra lines that we drew in, is that new graph still planar? Remember what planar means. Planar means none of your edges cross. So did any of these edges cross? No. So yeah, it's still planar. I'm not going to lie, mucking about with the unbounded face has a tendency to mess with people's heads. It's way easier to picture what's going on with the bounded faces, which is why we did them first. But notice here in terms of faces, we still have the 2 bounded faces that are degree 3. We now have a new bounded face that is, touched the wrong thing with my hand. A new bounded face that's also degree 3, and the unbounded face now is 1, 2, 3, also degree 3. So it turns out that this is actually a true statement that you can keep on adding edges until you get every face here is degree 3. And once you're at every face is degree 3, here's the thing that we are assuming, and I realize I didn't add in, and you guys have a tendency to think about them, a simple graph. So that would be as many edges as you can put in before you get into a multi-graph with the multi-edges. It's also one of the reasons we're jumping down to degree 3. A face with degree 2, really, that would be where you were dealing with a multi-edge involved. Okay? This can also be called triangulation of a graph. I don't think we're going to get to that anytime soon. But that would be sort of the idea of what you would keep doing. Now, let's check to see if the relationship between vertices and edges makes sense. How many vertices were in that teeny tiny little graph to the side? So remember, multi-edges are edges that have the same endpoint. Ooh, I see what you mean in terms of a multi-edge up there. Yep, technically you're right. We do have a multi-edge involved with that graph right there. So I'm going to go ahead and strategically cross this one off. Oh, no, I don't need to cross that off. I need to change the edge. Just a second. Let me fix it. But here's how you change that edge to make it not a multi-graph. Didn't think about that enough when I drew it. There we go. Now you got it, so it's still a simple graph. Where was I? Right. So if you look at the number of vertices in that teeny tiny graph, there's 4. If you count up the number of edges, notice what happens. You've got a grand total of 6. So let's see if that actually worked. So 3 times 4 is 12, minus 6 is 6. So yeah, we have the maximum number of edges according to our inequality and still having a planar graph. Now, all of this was just by way of an example to illustrate what you would do in a specific example. This doesn't explain why this is true in any old graph. I mean, it gives us the idea, but let's be a little bit more formal. So this is really the first time that we've done anything slightly formal in terms of a proof. So I'm just going to do an outline of why this works. But this would be, if you put it together a little bit formally, this would actually turn into a proof. Okay? So why this works is my tagline of saying I'm not going to be super formal with a proof. So first thing we did is we went ahead and we did an example to prove to ourselves it was something we could do. Then we actually want to start listing out things. And to the side over here, let me go ahead and list out our formulas that we had. So our formulas that we've had were Euler's formula, which we're totally going to need, number of faces, minus vertices plus 2. We've got the inequality we like, although this time it needs to be an equals according to the actual question itself. And then we also have those degree sums. So here we've got the sum of the degrees of the vertices equals 2 times the number of edges, and I'll write it in the same notation as Euler's formula right here. And we can do the same thing with faces. Now notice what this gives us. This actually automatically gives us, if we're trying to shoot for triangular faces or degree 3 faces, that means we're looking at potentially having 3 times the number of faces equals 2 times the number of edges. So that would be the reinterpretation of that last degree sum. Okay. So here's the idea. And I'm going to do it in sort of 2 columns. And not 2 columns citing reasons, but 2 columns of there's 2 different things we have to worry about at each time. So the first side is we're going to be dealing with Euler's formula. So dealing with Euler's formula says that if you're in a planar graph, you better have this relationship. Well, what do we know in Euler's formula? So let me title this. Euler's formula. Okay. Well, we know that the number of faces is, well, we have no clue how many faces there are. But we do know that the number of edges is supposed to be 3 times the number of vertices minus 6. Again, we have no clue about the number of vertices because this is supposed to be essentially an arbitrary graph that is both connected and planar and has a maximum number of edges possible in that scenario. Well, let's simplify that right-hand side. The number of faces, once we simplify the right-hand side, is twice the number of vertices minus 4. So that gives us a relationship between number of faces and number of vertices. Now on the other side of this squiggly line is the given information. So we were given that we were supposed to have the number of edges was 3 times the number of vertices minus 6. Well, in this particular case, what I'm going to do is I'm actually going to build to something nice. So this is really like scratch work to the side here. I'm going to double the number of edges, and I'm kind of going where you think I'm going. So if we double the number of edges, we're just going to double the info on the other side too, and I totally should have done it in one step. There was no need to do that. Oh well. So this tells us that we actually have 6 vertices, or 6 times the number of vertices minus 12, and this is really the thing that we actually needed. I'm going to go ahead and factor a 3 out of this. Weird but true, right? Now, anybody have a guess why I factored the 3 out of that? Totally a sneaky trick. The 3 does originally come from the fact that we're trying to get all the faces to look like triangles. True. There's another reason. Yep, that's the other one. The key thing here is we want to get some sort of relationship between E and F, so the number of edges and the number of faces. And this here, the 6 vertices minus 12, that is exactly the number of faces, but multiplied. So yeah, by factoring out the 3, we actually get exactly the expression that we have for the number of faces. Now, why would we want to do that? Because over here to the side, and let me underline it in orange, this is actually our goal. So that's the thing that if we can reach the expression that 3 times the number of faces equals 2 times the number of edges, we'll have actually gotten to the conclusion here. So remember, in terms of proof, and you guys have said that most of you have done a proof before, you've got a starting point and an ending point. Well, our starting point was a planar graph, so we could use Euler's formula. And our starting point was also that the number of edges equaled 3 times the number of vertices minus 6. Our ending point was that every face was triangular. So our ending point was this degree 3, which apparently I forgot to write down. So degree 3. And that meant if you had degree 3, in terms of a relationship, we were actually looking for this 3 times the number of faces equals 2 times the number of edges. Now, putting all of that together, I'm going to go ahead and take the expression we just have right here with the 2e, and I'm going to rewrite it. So we have 3. I'm going to rewrite the part inside the parentheses with an f. And notice that is exactly the goal we wanted to get to. So notice what this means right here. So let's actually write this out in words. So this means that if you are dealing with the sum of the degrees of all of your faces, which is supposed to equal 2e, this tells you that you are looking at, here, the degree of each of your faces times the number of faces, if it's the same, equals 2e. So this tells us that the degree of each face has to equal 3 when you match the pieces and parts. So for every face. I think I have a little space. Awesome. So our conclusion here is, since we got this degree 3 for every face, this means that the faces are triangular. Okay. Now notice, we had the result as soon as we were below these orange arrows, the 3f equals 2e. Everything else was interpretation. So the only way you're going to get this 3f was if, when you're looking at this degree sum of the faces, that you actually had all the faces were degree 3, and then that gives you the triangular, because triangular is the descriptor implying that you have degree 3 faces. Please note it's not a formal proof. However, it does walk you through why the thing worked. Questions make sense? Kind of feeling okay with walking through that? That was less a find it and more of a why something works question. All right. Well, I have got exactly one more question for us in section 1.4 today. And this question actually has to tie in with the poll everywhere question that some of you guys have found. Okay? So if you didn't find it yet, actually let me share this with you guys real quick, and then we'll unshare it here in just a second. So this is the same location as all of the other ones. If you don't have it on an app, if you go to a URL, this one here would be pollev.com/sbirdsong, and you'll be able to see this guy right here. So one of the things that we're going to need in the next example is we're going to need to do some comparison with the complete graph on 11 vertices. So the 11 down there, remember, was the number of vertices. So we need to know how many edges, because we need to know both the number of edges and the number of vertices for our complete graph. But I'm going to let you guys think about that while I get the questions set up. And then when we get to the point where we need that answer, we'll go and see what you guys said. Okay? I'm going to go ahead and stop sharing this. Did everybody get the information they needed on how to get here? If no, some shout out, and I'll keep it up for a little bit for you. All right, I am not seeing any shout outs for no, so I'm going to stop sharing that so our the other screen gets bigger. All right, so this last example is talking about some graph, and that graph is on 11 vertices, hence our looking into the complete graph on 11 vertices. Okay? So what we want to do is we want to prove, and I'm just going to outline this proof. I'm not going to do a formal proof, but we would like to prove or show that if some graph has 11 vertices, then either that graph or its complement, or both, have to be non-planar. So at least one of them can't be planar. Okay? So let's see what we want to do here. So the first thing that we want to do is talk about graphs on 11 vertices. So on 11 vertices, what do we know about that? We know that all graphs, G, are going to be subgraphs of the complete graph on 11 vertices. You guys are almost, most of you have gotten answers so far, because we're about to need that. So what do we know about complete graph on 11 vertices? We know this guy has 11 vertices, and we also know it has a certain number of edges. And this is where we need the number of edges, so we'll come back and fill that in just a second, since I still see that some of you are working on finding that answer. Now, the other thing that we need to worry about is we're going to look at two things. First thing is we're going to look at what half the number of those edges are. But since we don't have an answer yet for that, we're going to wait and fill that in just a second. And the other thing we need is if we're trying to look at whether a graph is planar or not planar on 11 vertices, we do have that inequality that relates edges to vertices. Okay? So the inequality deals with E is less than or equal to 3 times the number of vertices minus 6. If that inequality is satisfied, that does mean you're planar, which means we need to look to see if G or G prime, one of them should not satisfy that inequality. So we know we have 11 vertices, so this is 3 times 11 minus 6. What is that, 27? That looks like 27. Okay. All right, it looks like most of you have a guess for the edges on the complete graph on 11 vertices, so let's go ahead and roughly see what you guys thought. I've got all sorts of answers. Awesome. One of those answers is totally correct. So I'm going to go ahead and hide that again. So the formula goes as follows. You take the number of vertices. So in our case, our number of vertices is, I'm not drawing, our number of vertices. Then you multiply what? Well, you want to connect, in a complete graph, you want to connect every vertex with every other vertex. So we're going to connect each of these vertices with every other vertex. No loops. So we're going to multiply it by all of the vertices that are not itself. Except what does that do? That's the sum of the degree of all these. So that would be transcendental divided by 2. So in our case, this would be 11 times 10 divided by 2, or we should have gotten 55 back. Now, when we come down and we look at half of 55, and I swear there's a reason for that in just a second. So we divide 55 in half. It's not going to come out evenly because 55 is an odd number. So this actually comes out to 27.5. So notice when we compare the number of edges in the complete graph to the maximum number of edges that you could have and still be planar, you'll notice, roughly speaking, your graphs that are allowed to be planar can only have edges up to about the halfway mark. Okay? So that was the point of these last two lines right here to show that, roughly speaking, if you're going to be a planar graph, you only have up to about half the number of edges in the complete graph. Now let's look at the three cases. So case 1. And there's no particular order for these three cases. So case 1 is, suppose your graph F is a planar graph. Let me go ahead and say both connected and planar. Okay. Then, what do we know? We know that the graph has to satisfy this inequality, so that means we have to go ahead and say that the number of edges in this graph G has to be less than or equal to 27. Okay? And that's that inequality from the corollary that we've been dealing with the last several questions. Now, that would be regular old G. But what about the complement of G? So in G complement, we're still going to have 11 edges because remember, complements don't change the edges. Still going to have 11 vertices because complements don't change the number of vertices. But anybody remember how many edges there would be in the complement? Anybody remember the tie-in between your original graph and your complement with respect to edges? Not the dual, the complement. Yes. I got multiple notations because I realize it's not a great way of saying that or typing that out. So in terms of the complement, if you take the number of edges in the original graph, let's do a different notation. So this would be the number of edges in the original graph has to be less than or equal to 27. Okay. Well, total number of edges in the complete graph, that was trying to be an 11. I realize it now looks like an N. That's trying to be 11. It's 55. Your complement is what? It's all the edges that were in your original graph. So it's going to be 55 minus however many edges were in this guy. So in terms of if we write this out, the number of edges in the complement graph would be 55 minus the number of edges in the original graph. Now, I don't know how many edges are in the original graph. All we know for sure is it's not more than 27. So if we convert that into an inequality, because there's a range of possibilities here, this actually tells us that the number of edges has to be greater than or equal to 28. Any guesses why I would pick on the number 28? Don't overthink it. Where does that 28 come from? Ooh, that's a good way of thinking about it. But yeah, I just subtracted 27 from 55. That's literally it. And any guesses why the inequality flipped? Well, as the number of edges in the original graph G, you go ahead and they get smaller. Well, remember, when you add the two edges between the two graphs, the graph and its complement together, it has to stay at 55. So here, what happens, as this number gets smaller, if the sum still has to stay at 55, the number of edges in the complement has to go bigger. So now, when you get this answer here that the number of edges in the complement is going to have to be either 28 or bigger. What does that tell you about the complement graph? You think it's planar or not planar? Yep, so this guy here would be non-planar, and it would be non-planar because the number of edges right there is bigger than that 27 that we said we needed in order to be planar, or 27 or smaller to be planar. Now, you can do the exact same thing with case 2. Case 2, suppose you say the complement graph is connected and planar. Well, if the complement graph is a connected planar graph, then we know that the number of edges in the complement graph is either 27 or fewer, and if we did any other symbols, say the number of edges in the complement graph less than or equal to 27. So then if you looked in the original graph, now here's the fun part. If you started with a complement graph and then you went to the original graph, what's the relationship between those two? If you complement a graph twice, any guesses what happens? That's another way to think about that. Yeah, you go back to the original graph. So if you started with a graph whose name is the complement graph, and then you complement it, you'll go back to that original graph. So notice case 2 is really identical to case 1. The only thing we're going to do is we're going to flip-flop the symbol of G and the complement of G. That's literally it. So the complement of G is the original graph, which means the relationship of subtracting edges still holds. The other way to think about that is the sum of the number of edges in the two graphs has to always equal 55, which means we'll get the same inequality that the number of edges now in G has to be greater than 28, which tells us what about that original graph G. What conclusion should we come to? Should it be planar or not planar? And it should now be not planar. Now, technically speaking, we could actually end here because there are 4 cases. Case number 1 is G is connected. Then G complement could either, not G is connected, G is planar. Then the complement could be either planar or not planar. We said that there's really only one case, it has to be not planar. That really means they can't both be connected. So that eliminates one possibility right there. Case 2 is, well, flip-flop in terms of who's planar and who's not planar. So the complement's planar, the original graph is not planar. The only other case that could happen is if both graphs are not planar. But according to our sentence, we're totally cool if both graphs are not planar. But let me go ahead and put in that third case. So case 3 is if both G and the complement of G are not, actually technically speaking, you can look at here, it's not connected, not planar. So, example. Now I'm going to do the extreme example. Suppose you've got this guy. 1, 2, 3. So notice it's going to be a not connected graph or a disconnected graph. 3, 4, 5, 6, 7, 8, 9, 10, 11. So this guy, this is G. Now, anybody guess what the complement of G has to be? Yep, this would be the complete graph on 11 vertices, which I am totally not drawing. So over here, you have a disconnected graph. Over here, you're going to have a connected graph, but not planar. So remember, case 1, case 2, we assumed that one of the two graphs was both planar and connected. if you start having a graph where you have some disconnected stuff involved, that graph could be not planar, but it could also be where this guy is disconnected in planar, and then the other one would be non-planar. Okay? So that would be the case, the other case, and I'm going to go ahead and just brush over that one a little bit. Now, that totally takes care of section 1.4. I don't have any more examples prepped up for that section. The plan for the last couple minutes for today is to give you some of the key definitions in the first section in Chapter 2, and then we're probably going to have time to look at one example. So any questions before we convert over to Chapter 2 material? Or I guess I should say jump over to Chapter 2 material. All right, I'm not seeing any questions from you guys, so I'm going to go ahead and jump over to the Chapter 2 material. So Chapter 2, the first two sections of Chapter 2 deal with specific types of cycles, circles, paths, and trails. There's two different naming. There's actually a bunch of different naming conventions for these types of things. The buzzwords that you want to watch out for is watch out for the descriptor Euler. Okay? And that's going to be this type of one. If you look this up online, the second word here is going to be all over the place. However, here's what it means. So if you're looking at an Euler cycle, we're looking at a cycle which is going to visit all the edges of the graph. So this is the key thing. We are actually, let me put that in a slightly different color so it's easy to pop out. We want to visit all the edges of your graph. Now, remember what a cycle is. A cycle is starting and stopping at the same point. You go around your graph, and you have to come back to your starting point. That is the key thing. Please note, if you actually visit all of the edges of your graph, you will by default, no, the graph is really weird. You will pretty much by default be forced to visit at least one vertex more than once. So just as a comment down here, let me just note that all vertices will be visited at least once, and you're probably going to have at least one or two of them where you might have to visit it a second time. Okay? So that would be an Euler cycle. Now, an Euler trail is the exact same definition, except we're replacing the word trail with the word cycle with the word trail. So this is a trail that visits all the edges of a graph. And again, with a trail, it doesn't matter if you ended up having to visit your vertex more than once. You had to have the edges that you were traveling down had to cross over each other. In both of these two guys, you're not allowed to use an edge more than once. So you're going to visit each edge exactly once. That's the key thing. Those are the two main definitions of the entire section. It's a really short section. Now this idea of these Euler cycles and Euler trails actually came from, go figure, Euler. And this is a setup of how he came up with this problem. It turned out that he was in Königsberg, city with rivers. So this is a very, very rough, very old sketching of the city. And for whatever reason, he would walk around the city. And the city actually has 7 bridges, and you can just barely see them here. There's a bridge right here, there's a bridge right there, there's a bridge right there, there's a bridge right here. There's an island right here in the middle of the river. There are 4 bridges. And then there's a second little peninsula or island. You can't actually see that it closes here, but in other drawings it actually closes. It is a second island. Not that it actually matters for what we're about to do with it, but anyway, so this second piece also has a bridge to the mainland, has a second bridge to the mainland, and then there's one bridge that didn't show up very well in this picture between those 2 pieces of land inside the river. Okay? So he's walking around the city, and the question that he starts to ask is it possible to cross each one of those bridges exactly once? And the underlying assumption here is you leave your house, you go for a walk, you cross each of the really pretty bridges, because apparently they're really architecturally beautiful. You cross each of the bridges exactly once, and then you come back home. So that was the question that he had. And this actually was one of the questions that started off graph theory, because if if you read about this, one of the things that apparently he said in one of his letters was that he thought it was a geometry problem, but it didn't match with any of the geometry that anybody knew right then. It turned out that that was actually one of the first questions that bumped graph theory into existence. So let us redraw this outside of a sketch of like an old map into how you might draw this as a map. Okay? So our goal here is we want to cross each one of these bridges exactly once. So in reference, or to put it into the same terminology of the Euler Cycle and the Euler Trail, which are named after Euler, we'll go ahead and we'll draw the bridges as edges, which means these pieces of land, we'll go ahead and represent them as vertices. Let me actually zoom this out a little bit so we can see the picture just fine. Okay. So if we redraw, we'll have that middle island, and we'll go ahead and call that middle island A like it's labeled in the picture. Then we have the riverbank that's on the very top. We'll call it C like it's labeled in the picture. And notice there's two bridges between the island A and the top riverbank. Then we have the riverbank on the other side of the island. It's labeled, it looks like it's labeled B in the picture. And notice there's two bridges between the island and that side of the riverbank. So that takes care of these four bridges. Then we have the other little peninsular island, and it looks like that one in the picture is labeled D, so I'll go ahead and label it D. And there's three bridges connecting this piece of land to both the riverbanks and the other island. There's one bridge to the other island and one bridge to each of the riverbanks. So here is the rewording of the question. Does there exist an Euler cycle in this multigraph? So what do you guys think? And you can look at it either in the picture or in that little multigraph. If we start at one of these four vertices, little island, bigger, I'm going to go with island, or on one of the two riverbanks, was there any way for him to take a walk and travel down all of the bridges, so go through all of the edges exactly once? What do you guys think? Oh, I've got multiple votes for no. So the claim is that this actually, I'll write down the claim. So the claim is no. So for example, if we actually tried it, and let me go ahead and highlight, actually, that weird bubble one that we did earlier worked very nicely. So maybe we start at, I don't know, B. So if we start at D, go to B. Well, we can't go back to B on that same bridge because that would be using the bridge more than once. But we can go to A. We can go to, I don't know, maybe you want to go back to D now. Maybe you want to come back to C. At this point, you could go C to A. You could go C back to B. And we actually were pretty decent about collecting most of the bridges there. I'm highly impressed with myself. But now that we're at B right here, is there any way that we could go back and pick up that bridge that we didn't get to from A to C without crossing any other bridge more than once? And I know you're all going to tell me no. Why? Because we've already traveled on all of the bridges leading off that riverbank B. Okay? But it does turn out in this particular graph, it is not possible for an Euler cycle to exist. In fact, just trying to find the way to get to all the bridges, even if you didn't want to come back to your own starting point, looks difficult. Okay? But it turns out there was a conjecture that Euler made, which has been proven. And what he said is if you have a multigraph, then, and he didn't use the term Euler cycle, but we'll take the terminology that we have now. In a multigraph, it's going to have an Euler cycle if and only if, or exactly when, first of all, it's connected. If your graphs aren't connected, and let me real quick draw a picture of a not connected graph. Anybody have a guess on why the graph would have to be connected in order for an Euler cycle to exist? Don't overthink it. Yeah, you can't get between those disconnected parts. The first thing is sort of obvious. You have to have a connected graph. And here's the part that's not obvious at first glance. You also have to have all of your vertices to have even degree. So let's do a quick check up on this multigraph that we were just looking at. If you look at the degrees of the graphs, do those degrees, are all of them even? What do you guys think? If you looked at the degrees of these vertices, are they all even degree? Yeah, it's worse than no. It's none of them are actually even degree. But it turns out in this case, nope, there's no possible way to build an Euler cycle here. It turns out the reason you need even degree is because you need to be able to go into a vertex, use an edge, and then leave the vertex using an edge that you haven't traveled on yet. And the only way to always be able to do that is if you have even degree, because you'll always be able to go both in and out on an even degree vertex. It doesn't have to be degree 2, although that's the simple case. Degree 4 would mean you'd have to visit the vertex twice because you go in and out 2 times to handle all 4 of those edges. Now, I'm going to go ahead and stop us there, but we were at the beginning of next time, we'll go ahead and start with this example where we've got a graph that looks a little bit intense, or maybe we'll pick a different graph, and we'll actually check to see if we can find an Euler cycle on this graph if one exists. Okay, so that's the snapshot in terms of the Euler cycle and trails. The key thing to take away is if you see the word Euler, it is referring to edges, and you want to be able to grab all the edges. Okay, but that's it for today. I'll hang out if you guys have any questions, but that's it. We're done. I don't have anything else prepped for you guys for today.